In this lecture we're going to look at the standard normal probability distribution. The normal probability distribution, as you may have heard the term before, or the bell distribution, the bell curve, right, all refer to the same thing. So in general, the normal distribution looks like this. Now this is our first continuous distribution. And actually it'll be our only one because that's the one that's most important to statistics and to us. It's continuous in the fact that if we ask for the probability that x is exactly one number, that means 2, say, for an example, that's 2, 0, 0, 0, etc. The probability of that is essentially 0, right? It's like dividing 1 by infinity. The normal curve itself is symmetrical around its mean, and so we would have a distribution of x's symmetrical around its mean. The total probability of the under this curve is equal to 1, therefore there's a half on both sides of the mean since it's symmetrical. Since there's half on both sides, by definition then this mean is also the median, right? The median is defined in our first module as the point at which 50% of the data, half the data lies below and half the data lies above. So with any symmetrical distribution, and the normal is just one example of a symmetrical distribution, the mean and the median are the same. But also, while we're at it, since that's the top of the distribution, this is also the mode of the distribution. Okay. Alright, well it turns out, alright, to remember, well, just as a sort of to give you some perspective, we didn't just have one binomial distribution or one Poisson distribution. We had distributions for the binomial that depended on its parameters n and p, and we had tables to work that out, or formulas to work that out. Well, it turns out that all normal distributions are scale factors of each other. Alright, so all we need to have is a probability distribution for one normal distribution, and then we could work out the probabilities for any other normal distribution. So what we do is we standardize the normal distribution to a distribution where the mean is 0 and the standard deviation is 1. Alright, and this is called the Z distribution, the distribution of standardized normally distributed values. Okay, so this is the standardized or standard normal distribution, and any normal distribution can be scaled back to this distribution, just like degrees centigrade can be scaled into degrees Fahrenheit, or yen can be scaled into dollars. Any normal distribution can be standardized back to this distribution, the standard normal distribution. Alright, we have tables that help us calculate these probabilities, right? If we had access to Excel all the time, we could always use an Excel function to do that, but we will use tables. It turns out that our tables give us the probability between 0 and some limit. Right now we'll call that Z star. Alright, so we'll find the probability of getting a generic Z value between 0 and, say, a value, particular value Z star, and this will be found on the tables. Notice or note that as this is a continuous probability distribution, it does not matter if we use equal signs in our limits or not. This is the same as the first probability. Because as I pointed out above, with any continuous distribution, the probability of getting exactly some value is 0. Alright, so we do not have to worry about our limits with a continuous distribution as we did with our discrete distributions, binomial and Poisson, etc. Okay, let's have a look at the tables. Alright, so this is the normal distribution table that we will use. You'll find it on the website. You can download it and print it out. Alright, and this type of table will be new to you. Right, the distance past when we didn't have calculators, for instance, we'd have need to do multiplications of difficult numbers. We'd use logarithm tables, log tables, and log tables would look like this in a sense. Alright, so let's learn how to read this table and how to use this table to our benefit. Okay, so let's say that we're looking for the probability of getting z between 0 and 0.8. Okay, again, sometimes you'll find it useful to draw a diagram. In this case, we know that this we will find from our tables. Alright, 0.8. Okay, 0.8, the value for that probability is there, 0.2881. Alright, because we have the first part of the value 0.8 there, and this will add to the 0.8, alright, but that's still 0.8, and so our value, as I pointed out before, is 0.2881. Alright, let's say that we wanted to find the probability of getting z between 0 and 0.86. Alright, it's a little bit further. Alright, it's going to be out here. So the probability is going to be larger, right? Again, we can look that up from our tables. Alright, it's not going to be this value. We'll look at the 0.8 row here. Whoops. The 0.8 row. Where my cursor is in the 0.06 column. Okay, and that value is this. Alright, so we're in the 0.8 row, the 0.06 column, and so that's the value of getting a z between 0 and 0.86. That's 0.3051. And as I pointed out before, that was larger than our first probability. Well, what happens if we want to find the probability of getting a z between negative 0.86? Sorry, I put an equal sign there, not that it matters, and 0. I'm not going to confuse the matter right now. Well, since the distribution is symmetrical, around 0, if I go to positive 0.86, and this is of course not drawn to scale, right? These two probabilities are identical, so the answer is still the same, 0.3051. So that's why the tables only give you for values from 0 to some positive number. If we want to put some negative number, well, we ignore the negative number because the table is symmetrical.